Good morning, class. So today we are going to discuss a new topic known as clustering. It is important because now we are going to moving out of the territory of supervised machine learning, which I've been covering most of the time until now. And what we are going to learn today is a technique known as the unsupervised learning. So what is clustering? So here is a graph that shows you a typical task in the problem of clustering, right? So here, unlike in the supervised machine learning, remember in the past when we do regression or classification, the training data points are like, I gave you X and Y, right? And we have N data points. And then your goal is to learn a function of X which predicts Y, right? And in here, if you look at this particular data set, I didn't give you any label, therefore your data points will be only the X, okay? And then clustering is about answering questions like, how do you group these data points? And how many groups there are? And then what's the right algorithm to find them? So let's take this particular data cloud as example. One obvious way is to say, maybe there are two classes like this, right? If you visualize them, you can group them very easily. But someone could also argue that maybe there are three classes, right? Or maybe even there are four classes. And when you are able to visualize the data like this in two-dimensional space, you don't need an algorithm. You can just plot them and then use your pen to draw a boundary. But in real world, your data are like a set of image with a couple of thousand images, and sometimes texts. If I give you, for example, 10,000 books, it will be very hard for you to read all of them and then to cluster. It's time consuming. And the visualization is impossible because they are living in a very high dimensional space of pixels, and maybe words, right? So today we're going to talk about a algorithmic way of solving the clustering problem. So here are some more words about exactly what clustering problem entails, in statistics, in machine learning, and also in our natural science research, right? So here, for example, the process of grouping the objects into classes is by itself an interesting algorithmic topic. You need to answer the questions like how to enforce a high intra-class similarity. Points within a class are similar to each other, and then points between different clusters should be less similar. And this is basically, to be achieved without any supervision. So I just told you what is already the contrast between a supervised machine learning and unsupervised machine learning. So here, I made it a little bit more formal. And this task is, in fact, maybe the most common problem, in our scientific research. In science, instead of education, science is about the discovery. So you often run into data that is of unknown nature. For example, if you take, say you are an astrophysicist and you have pictures from the Hubble telescope of the universe, and you don't actually know exactly how many stars you're going to observe and how they form into systems, right, celestial systems. And then you rely basically on a clustering algorithm to identify patterns out of it. Here I have some easier pattern for you to recognize. Again, when things become graphical and able to plot, it's actually easy. But imagine that now you either are facing a much bigger data volume so that you have not just a dozen kind of points, but say millions of points, or you run into a much higher dimensional problem, then you really are going to face a challenge. But here, just to make a intuitive sense about what do we mean by, say, intra-cluster similarity and inter-cluster dissimilarity. These illustrations can give you a kind of a concrete sense, right? You can cluster people, image and language and the natural species. And there are these issues I just mentioned about the algorithmic issue of, maybe in fact the philosophical issue about how to define groupness, which I'm going to discuss in a second. We're going to also study, the very mathematical formula behind the notion of similarity and dissimilarity, how to make sure that two people, when they see the same data set, they will be reaching to the same conclusion in terms of distances and the similarities between them. That's why a mathematical formula is going to be very important. And then, in fact, the representation of objects will also be very important. Sometimes you will have an alternative way of representing, a data points. Say, for an individual, how do you represent them? You represent them by their name or by their biometric, right? So we are going to discuss formally, some plausible representations. And there is also a very, very deep issue in terms of how many clusters. Do you fix the cluster a priori, or do you let statistics to guide you to find the optimal number? Again, there is an open body of research for this topic. Most of the machine learning research on clustering focus on algorithm. How do you develop heuristics, sometimes with or sometimes without guarantee, to discover basically the clustering based on the definition we have above on distances, on number of clusters, and so forth. Right. And then, of course, finally, with the algorithm in place, you can also start analyzing complexity, convergence behavior, and so forth. So today's lecture will be a very high-level overview on all these topics, but with just a very, very, how should I say, superficial touch on some of the points. The field itself is actually a lot deeper, and maybe in our future lectures, we're going to choose a few angles to study them in depth, such as the EM algorithm we're going to discuss in next lecture. So what is the natural grouping among things? It's a very subjective thing, right? I give you, this, of course, is a picture that many of you are perhaps not very familiar with. In the good old days, one of the fun thing people do after dinner is to watch a movie series called Simpson. And here are the characters, in the Simpson movie series. And now I just put their cartoon, on the screen, and I asked you to cluster these people. Again, we already can run into some debates, right? For example, for people who are very familiar with this movie, they actually may know, who are the folks belong to the family of Simpson, right? He has a wife, and he had a few kids, and so forth. And then their kids go to school, therefore, and maybe there are other, people in the employed by the school, which belongs to another class, right? You can definitely, find a natural way to group people based on whether they are Simpson family or not. But for people who never watched the movie, all the story I just talked about make no sense. But still, you could naturally group people by their gender. All the females go together and all the males go together. You may even try to find patterns of their dresses and other things. Right? So it's a very subjective thing. Therefore, we have to agree on a few things before we can even compare a clustering algorithm. Well, one thing we agree on is maybe to define similarity. Okay, we're going to really say, let's already agree that we're going to cluster people by their family affiliation or their shape. But then the similarity, for individuals or for items within the class is actually an open topic, right? So here, I put you next to each other two pictures, right? Well, I guess for a human eye, we probably can easily, see the differences between them. But if you turn them into a pixel level feature map based on, say, color histogram, or based on some kind of wavelets and other things, and throw at them at an algorithm, you can easily see a reason the algorithm being confused, because at least for the color histogram, they are almost identical. Right? So again, this similarity is another philosophical question. We have to come up with a pragmatic approach to really define what we measure, right? And on what representation we measure between distances. So that's basically how we start formalizing the problem of clustering into a more principled and explicit mathematical foundation. Okay. So here, let's start with the definition of the similarity and start to introduce some formal notion of distance measure. So that, and what do we mean by a very qualified distance measure, that we can use them pretty explicitly and robustly to define distances and the similarities. So here are some of the key properties people expect from a proper distance metric. Okay, the first thing is known as a symmetry. That if you measure the distance between two objects, the way you plug in, the argument in the equation shouldn't be the order of their plug-in shouldn't be affecting the outcome. Right? And also, if you measure the distance between the same thing, then there should be zero distance. This is a consistency of self-similarity. You must be unequal to yourself at the same time. Okay. And then there's also a thing called positive separation, that the distance between two objects are zero only and only if and only if they are the same thing, if they are equal by your definition of their metric, their feature. And then there's also a triangular inequality, which says that distance between A and B must be smaller or equal to the distance between A and C and C and B. Okay, so there are some natural arguments about why these definitions are necessary. For example, if you really violate the symmetry, then you will find an awkward kind of a condition where a person says Alex looks like Bob, but on the other hand, Bob looks nothing like Alex. This is a very, very contradictory statement. And there are a few other kind of awkward statements that you could derive if such situations are violated. Okay, so I'm not going to read all of that, but you can hopefully find them to be already self-explanatory and intuitive. So what are the metrics that satisfy those conditions? Okay. So here I'm going to show you a broader class that you rarely need to go beyond. There are other metrics, but I guess we are going to focus on the mainstream, common metrics. Imagine that you have the representation of the data points to be a vector, say x and y. It is a p-dimensional vector. Each of the x of I is a dimension of the data, say a pixel in an image or a word with their frequency in a document and so forth. Then the Minkowski metric is basically defined as the following. It's the r's root of the sum of r's power of the differences between every dimension. Okay, kind of intuitive. If this sounds a little bit too kind of unfamiliar, you can actually replace this r, okay, with some real numbers and that will turn you something familiar. For example, if you let the R to be 2, then you arrived at something called a Euclidean distance. Okay, and I have a graph in the next slide showing you how the Euclidean distance look like. If you turn the R into 1, then you get a distance known as the Manhattan distance. And if you set R to be positive infinity, then you have something called the max distance or sup distance. Okay, so how they look like? This is the intuitive thing. The Euclidean distance is this one. Basically, it's the straight line connecting the 2 points. Okay, and the Manhattan distance, by their name, you can imagine that it's like when you want to get from destiny 1 to destiny 2 in the in Manhattan. They are this place is highly graded by blocks. Therefore, you cannot just cut into a block, right? You have to basically walk along the streets and the avenues to get to another point, right? Therefore, the distance is defined as this. The sup distance is a little bit awkward, but it will be useful. It's just a measure in whatever direction, the direction that gives you the maximum separation. Therefore, it is only this part, the block distance, or the distance between the avenues, right, in the Manhattan sense. Okay. And typically, a clustering algorithm will have the flexibility of choosing between all these distance functions, for whatever purposes they want to achieve. For example, very often in information theory, in communication theory, people use a distance called the Hamming distance. Okay, the Hamming distance is basically the Manhattan distance when the features are binary. Well, remember that in digital communication, if you want to send a signal, all the signals are encoded, into a 0 and 1, electronic pulse, right? And that basically, becomes the natural representation of a information, vector or variable, in communication theory, and that's why people use the Hamming distance to measure their distances so that you can start to group information and messages. Well, sometimes the distance I just talked about may still not work because it is really measuring some kind of distance, in terms of a length or differences along the dimension. But now here I have some new data sets, and you can take a look. On this graph, it is the measurement over time of the expression level of 2 genes. Okay, and this is again the measurement of the 2 genes a long time, and here another set. Now I want to ask, which pair of genes, or in which cases do you feel they are most dissimilar among these 3 possible scenarios? Let me open the chart. Let me see any. The last one look mostly similar. The bottom right. You think this is mostly similar? Yeah. I can see why you say that. I saw another answer, which says the top left. Interesting. So I can see both your point. You at least we have a consensus that this one, right, is not dissimilar enough. That's good. We have a consensus. And between this one and this one, we have a disagreement. Can one of you give an argument about why you think this is most dissimilar or this is most dissimilar? Maybe as accurate as possible, using some kind of a, if you will, mathematical characteristics. You can shout out or you can type, either way is fine.
Can we say that the first one is like negatively correlated? So basically you can just take the opposite of what, like if it's blue positive, then it's like the exact value but negative. So they're still like highly correlated.
Okay, thank you. That's an answer. She basically said that this one is literally, trying to, well, it is negatively correlated. It means that they always do the opposite thing at every time point, right? In my opinion, that's the best way that I can be against you, because whenever you say A, I'm going to say B. I'm going to always oppose you. So that means that you and me are completely dissimilar. Anyone want to say something about this? Why you feel this one is the most dissimilar?
There's no clear relationship between the two.
There is no what?
There's no clear relationship.
Okay, there's no relationship. Basically, B is indifferent about A, right? And also, if you measure the Euclidean distance and whatever distance function we defined earlier, this one may give you a pretty big divergence, because you can see the distance between them if you add them together can be quite big, right? Yeah. So that basically tells you, how interesting this problem can be. In fact, I don't have an answer. I think both of you make sense. At the end of the day, it's really about how do you want to, achieve a particular practical goal. Do you want to, for example, turn one gene to be agreeing with the other, or you just want to, have a quick, easy kind of measurement, on some of the behavior or other patterns, right? So at least for this one and for this one, if we're talking about their correlatedness, there is another way to measure them, which is known as the correlation coefficients. Many of you probably heard about that already, right? In statistics, one of the famous notion to measure the similarity or the relationship between two random variables is known as the Pearson correlation. Okay, it is mathematically defined by the ratio between the covariance of two random variables and the standard deviation, the product of the standard deviation of each of the random variables. Okay, but note that this is a definition over two variables. Okay, not two vectors. But the same kind of rationale can be applied to data vectors if you just treat, the vectors as samples. Okay, as samples from the data as samples from the variables. Okay, so that basically turns the calculation of the covariance and the variance into this sample-based algebra. That is also very easy to do. Okay, and if in a special case that your data is already centered, by the way, this x bar y bar is the mean of the sample of x and y, right? If the mean equals to 0, meaning that your whole data sample are centered, then this Pearson correlation could reduce to something known as the cosine distance. Okay, imagine that I have a system here, I have a point here, I have a point here, then I draw an angle, then the cosine distance basically is computed from this equation. Okay, so that gives you a sense about the relationship between two random variables. The correlation sometimes has a nice property, of being invariant to the magnitude of the data, but focus more on pattern, right? For example, imagine that I have two data points, two groups of data points. One is in in here, and the other is in here, for example. You can see that their magnitude can be very different. And maybe I have another point in here, right? So and another point that is in, so for example, in here, right? So if you measure the distances, you will see that these two are very close to each other, and these two are further to each other. But in terms of direction, they move the same way, so they may be similar. And by measuring the cosine distance, you can kind of normalize them to a kind of a unit ball surface, and then you can only compare their differences on the angle rather than the absolute length of that data sample. Again, it's based on your need. There isn't the right and wrong. It depends really on what you want to achieve in the class. Actually, I want to mention another distance, which is even more operationally interesting. Sometimes it's used. It's called the editing distance. For example, in these two individuals, when you compare these two ladies, why you feel they are closer to each other? Of course, they are both females, but the editing distance basically says that how many steps I need to do to turn from one kind of item to the other one. So here it says that you can change the dress color from blue to red. You can change the earring. It's a little bit harder to see, but they do wear different earrings. And the hairstyle need to be changed as well. That 3 steps makes you, turning Patty into Shima. Okay. And then, to get to this point, another lady, then, need to even do more editing, including, changing the heights and the body weights and so forth. So that kind of distance sometimes is interesting, especially when you run into discrete measures, such as, in Word document, that you have different words, and it's a little bit harder to measure, a numerical distance between 2 words, but more on the editing distance. Okay. And in fact, there is a whole discipline known as the distance metric, which will automatically find you the right metric, for your clustering, if you cannot tell, exactly what metric should be, but examples. Say, I know these 2 guys are similar, although I don't want to tell, or I cannot tell why they are similar. I just have a feeling that they are similar. And if you are giving 2 data sets, and you can kind of identify a few examples of such similarity or other kind of information, which are known as side information, you can employ an algorithm which discover automatically a mathematically clean distance function for you. So this is a topic I put in the appendix of today's lecture. If you have time, we can go over them briefly, but otherwise you can read it offline. Now, having the distance function being determined, and assuming that we also have, let's not assume anything yet. Let's say just only have a distance already. How are we going to group people, group items? So this actually leads us to discuss the clustering algorithm. Again, there are 2 very broader family of algorithms. One is known as the partitional algorithms, which is like this. Sorry. You basically start from the whole thing, and then you start to divide them into subgroups, and you can further divide them and so forth. Right? So this is called partitioning. And the other, there are some names, some algorithm we're going to study. For example, K-means algorithm, which is a very famous algorithm we're going to do today, is one example of the partitioning algorithm. And the next class, we're going to study mixture models. I have to say that partitioning algorithm is more favored over the alternative hierarchical algorithms due to many operational convenience, including convergence speed and so forth. Yeah. But before I go that, I'm going to cover the less favored one a little bit more because you will never see it again, probably in this class. So they are known as the hierarchical algorithms. It's a bottom-up algorithm. It could also be top-down, but the goal is to generate a hierarchy which touch upon which actually make explicit the relationship between every data points. For example, here you can imagine building a tree, right, over, say, a species that explicitly gives you a sense of relationship. For example, all the vertebrates, all the animals can be divided into vertebrates and invertebrate. And then invertebrate, you have fish, you have reptile, mammals, and so forth. Right? And invertebrate, you have worms, insects, and so forth. Right? So it's very useful, right? And it is very often the preferred way of representing knowledge. But on the other hand, it may not be necessary. For example, if you have 1,000 fishes, maybe coming from the same species in here, but they are different just by size or whatever other body metric, you may not be interested in forming a little tree of 1,000 leaves just for every fish, right? So that's why a hierarchical algorithm is not very popular or practical when you handle really large real data set. Okay. But at least we know how to make that happen. There are still some instances which even though big, but still use hierarchical clustering. Yahoo still exists, but in the good old days, Yahoo is the preferred kind of portal for search engine and for web browsing, and all their pages, at least in the past, were organized in a big hierarchy. Okay, I don't know whether they updated it now already or not, but that's what I know from the past. So how do we do clustering algorithm? In fact, another way, maybe advantage of the hierarchical algorithm is to, allowing you to produce something called a dendrogram, where, the distances between, every element and every, super element, say a group, or, a latent entity, can be both represented and also be quantified. So this dendrogram is about the names, of or the form of the name Peter, in different languages. And you can see that I'm not an expert in language, so I don't know which language. I believe this maybe is a Slavic language. Maybe we have also the Latin expression and so forth. Right? You can see that they, this dendrogram show you the distances between them. If you show me a dendrogram of, in the bio species, I guess it's easier for everybody to tell, how far they kind of diverge in the history, and what the ancestor may look like. But having a dendrogram makes the clustering very easy, because you can pretty much just say draw a threshold in here, and once you draw that, you literally can start to see the data falling into different clusters. Right? Yeah, I think I'm right. So in here, the blue stuff, the green stuff, correspond to the Latin kind of language community, and the red ones indeed are maybe Slavic. Right? Okay, so how do we design a algorithm for hierarchical clustering? This is actually a very non-trivial thing, because the hierarchical clustering need to touch upon every data point in a very non-trivial way. And first, you want to probably say start from every object being in its own class. That means that you started from a singleton cluster. Each one has one member. Then you may need to start joining the closest pair, okay, into class. Maybe join these two, and so forth. But how to join them? You need to compare the distance between the candidate pair. That means you need to compute the distance between every pair of the data, right? So that probably should already sound alarm bell, because comparing the distance between every pair is already an n-square operation, which is pretty expensive. And when you have a data set of, say, 1 million data points. If you do 1 million square operations, it's going to be very prohibitive. Right? There are algorithms which can be a lot cheaper than this, but still give you a clustering algorithm. And that's why we're going to discuss some other, non-hierarchical approaches. Top-down, could give you a little bit potentially advantage in computing, but if you want to do a good job, you still need to do this kind of pairwise computation. Okay, so we just talk about the issue about measuring distances, but this distance measure or the closeness measure is in the case of a hierarchical clustering, is not just between pair of samples, right? Because if you reach to a level of 2 clusters and multiple clusters with each of them with just a few number of data points, you need to further to aggregate them. That requires you to compute the distances between 2 clusters. And again, there are multiple strategies. Here, I give you 4 such instances. One is known as the single link. Okay, it basically tells you to measure the closest neighbors, between the 2 clusters. Maybe there is a point in here, there's a point in here. Then these distances is the distance between the 2 clusters, right? Well, complete link is the opposite, right? You measure the member that are further to each other, this one, right? And the centroid, you compute a center, and the average, it's intuitive by their name. So I will show you an example about how this different definition will affect you, the result of the clustering. It's kind of interesting. First of all, you need to compute the pairwise distances between all of them. That's actually where everything began. It's a very expensive operation. Say it is given. I have these 4 points, and their pairwise distances are all computed. Okay. And then let's say we want to use the Euclidean distance. Okay, so, and these are the numbers I could pre-compute. Now let's look at the single link. By single link, I need to first join the closest 2 points, which is 2. Therefore, A and B form a cluster. Okay. And once A and B form a cluster, this table gets reduced into, a table with 1 cluster less. Therefore, this is a cluster, and the C and the D are potential other clusters. Now, how do you merge them? The single link says that you measure the distances between, this AB cluster to C just by looking at the distance of this point and that point. Okay. And also you look at the data point of this one and that one. And therefore, maybe this one is closer. Therefore, you group A, B, and C together. So that's basically what achieved by a single link. A complete link is a little bit, more interesting, right? Here, you are measuring the distances between AB, or between C to AB and C to others using, what is known as the complete link, meaning that the distance between AB to C is from this point to that point, which is further than the distance between C and D. Therefore, you are going to group C and D together first. Okay, so isn't that interesting? You are not having this group and that group, and then you are going to continue to merge. Right? So this distance function does actually affect the way you actually come up with a cluster solution. And that gives you 2 different dendrograms, which kind of gives you interesting insight into how data are related. And okay, before I move on, I want to remind you about the computational complexity. It's an expensive measure. You need to really start by computing, the pairwise distances. Okay, even before you start the first step. But then you need to do the agglomeration, the hierarchical kind of division or aggregation. That means you need to redo such a distance calculation, on and on. depending on how you do it, if you have a smart algorithm, sometimes this computation can be a kind of table look after kind of procedure, and then in constant time, then your whole procedure will be optimally n squared. But very often, you may run into a naive algorithm. Then you need to basically do a, you need to run into a log n times n squared or even a n cube algorithm, so that every time you just recompute everything basically, right? So this is an expensive algorithm. So to remember, when n gets big, this whole algorithm basically breaks down. Partitioning algorithm is very similar, so I'm going to skip about that. Okay. If you want to do partition in an exhaustive way. But today I'm going to talk about a slightly different partition approach, which is taking advantage of some algorithmic tricks and some of the statistical properties. So in partition, let's say we decided at the onset that we're not going to reach down to the bottom of every data points. We're going to only group or partition the n data points into k clusters. Okay. And then our algorithm is trying to find the best way to group the points into k clusters. And one of the most popular and the most intuitive algorithm is known as the k-means. The k-means is a very important algorithm which gives you a number of insight into algorithmic analysis and complexity analysis and statistical properties of unsupervised learning. So I'm going to give you a little bit in-depth description of this algorithm. So here is the pseudocode of that algorithm. Okay, as input you have the data points xi only, and I equals to 1 to n. Okay, it's a data point. And then you also are given a value k, which is the total number of clusters. Okay, then you run into a key initialization step. Okay, you are going to randomly pick either 10 points from within the data set or k imaginary data points that you just want to plug into the algorithm. Okay, so these are called the centers, okay, which are randomly initialized. You have two ways already, or maybe a combination of these two ways to initialize these centers. And then what you are going to do is that for each of the center, you are going to well, let's see. Yeah, you are going to now compute which cluster they need to go to. For example, I have these few centers, and then for a new data point xi, I need to decide whether they go to this center or that center or that center. And this is done by measuring the Euclidean distance. You just compute the distance of this particular data point to every center, and then you make a label. Okay, and then after all these n data points are assigned to every cluster, you are going to now re-estimate these k cluster centers, and obviously the center will be different from where you initiate them, right? And then you are going to repeat this step to reassign the data points, and then we're going to see when things stop changing. Okay. Just to make sure that you get what I just said, I'm going to give you a more kind of intuitive graphical illustration. Let's say we have all these initial data points to be the blue diamonds. Okay, and I pick 3 centers random, and here are the 3 centers. By the way, my k equals to 3 in these cases. Okay, and then what I'm going to do is to now compute the data points, to compute distance of every data point to the center. Okay, this will be done on every data point, and then accordingly, I'm going to assign them a cluster label. Okay, I call this a red cluster, a green cluster, and a blue cluster. And you can see intuitively, how their colors are labeled. And once we have this initial line assignment, I'm going to now recompute the center. And as a result, because most of the red points are here, the center position will move this way. And likewise for the green centers and for the blue centers, right? So I will be entering the next iteration with this configuration, the new centers. And then with the new centers, all the points will be reassigned based on their distance to the new center. For example, you can imagine that this green guy here, right? Originally they were green, but now with the center of the green cluster moved leftward, it becomes further to this point. But the red center actually becomes closer to this. So this one will be reassigned. What happened to this one? Well, I don't know. We will need to compute numerically, right? So at the end of the day, you have this reassignment, and then the center will move again. Okay, you can imagine that after many iterations, you will run into a situation where we call convergence, that the center stop moving. Okay, so that's the algorithm known as the k-means. It's a very interesting and easy algorithm. Hopefully you can implement all that using the loop and multiple loops, maybe in less than 10 lines of code, right? And just some background knowledge. This algorithm is known as the special case of a k-means known as the EM algorithm. We're going to discuss in next lecture, okay? And why this algorithm is converging? By the way, this algorithm will converge, okay? Well, the easy argument why it's converging is because we know EM algorithm is converging. Therefore, if k-means is a special instance of the EM expectation maximization, it should also converge. And I know this is a pretty lame argument because why you can ask why EM is converging, right? We're going to discuss more later, but just to give you a dose of that feeling, what we are exactly doing just now, which looks like a very heuristic, calculation of, averaging and distance and so forth, actually reflects what we know as a gradient operation. You are actually moving, the direction or the magnitude of those centers and assignments in a direction that is maximizing the gradient, and that is along the gradient of how things should move to minimize a loss function. The loss function is actually the overall intercluster distances of the points to their centers. But we're going to make it more formal in next lecture. There are some questions already. Will it necessarily converge on the same outcome each time? Well, yeah, Daniel actually answered already, depending on the initialization, right? It depending how you initialize, they may converge to different point. Right? And actually opens a deeper question. Do we do it only once, or we actually want to leverage on this opportunity of random initialization to actually drive for different convergence and compare different convergence? Yeah, I think some nice discussions already on how to initialize. Yeah, I'm going to follow up a little bit. But before I do that, let's also make clear a few other points. There is a measure of goodness of the cluster, which I just mentioned. It is the intracluster distance of points to the centers. Okay, so this is usually what a KM algorithm trying to minimize. In fact, statistically, they also correspond to the maximum likelihood kind of situation, when the data are assumed to follow a Gaussian mixture model. But again, I'm going to make the mathematics more clear in next lecture. And all algorithm just now actually at least guarantees one thing, that the reassignment will monotonically decrease this so-called SD measure. Okay, that's something you can prove by yourself. And that's why it is converging, because it is monotonically decreasing. They will converge. Do they converge to the global optimum or the local? That's actually a question. In fact, unfortunately, for this type of a loss function, and also more generally for the EM loss function, it is known as to be a non-convex loss function. Okay, what does non-convex mean? Well, just by example, or non-concave, I would say, depending on which direction you're looking at the problem. This is a concave loss, where if you start from somewhere and every time you move, you decrease the loss, then it will go down to the bottom. And this is called a global loss. Okay. Sometimes the loss function can be of a weird shape. They have valleys and little hills and so forth. Then, if you initialize in the wrong place, let's say in here, then the best you can do is to converge to here if your algorithm just keep minimizing the loss function. Because here, if you want to jump over this hill, you have to now allow increasing of the loss function before you go to a much bigger decrease. But that's not allowed in this particular algorithm, which we know as the gradient algorithm, right? And that's why analyzing the shape of a objective or loss function can be very interesting. And this loss function, by the way, is not shaped like a concave one. It is shaped as a very irregular one. Right? So that actually explains why we need a heuristics like what Daniel just mentioned, multiple initialization. If you, for example, if you are in such unfortunate situation where you have a very bad initialization, imagine that your initialization is that you pick 3 data points, which are here and here and here. I bet that you will be running into a convergence which will be not looking so nicely. Maybe everything, I don't know. I even cannot imagine what the eventual cluster look like if I initialize in this way. But it probably wouldn't be as nice as this. Okay, so what you can do is that you try this particular initialization, you try something else, and you try a couple of times, then you compare the resultant converging value of this loss function, and you pick the best one. Okay, so that's basically almost like a street smart kind of quality I would expect from you. By the way, I do run into PhD level machine learning students at CMU who does not realize that he or she needs to randomly restart the KM algorithm to get a better clustering, because the theory didn't tell you that. But in practice, you better practice, which will get you some very nice results. Okay. It's like in this case, you put a starting here, you put a starting here, you put a starting here, and the one of the start will drive you onto here, and you can have a chance to pick them up. Time complexity of this algorithm. Well, there is a reason for favoring algorithm like k-means, even if it has a risk of running into a local optimum. If you don't pick the random start often enough or lucky enough, you still can get stuck into a local minimum, but it's still maybe a plausible answer, not ideal, but it's an answer, right? But the cost you pay to reach the answer is not as expensive as a hierarchical algorithm I just mentioned. So now let's see how expensive to compare the compute distance. Say I have a data point x, which is a m-dimensional vector. Then a single operation of computing the distance between 2x, x and the x prime will be the O of m, right? And then you want to compute the distance of a point x to the centroid mu of k. And you have n such data points. And each of them need to compute a distance to the mu. That basically is k of n operations. Okay, so it's linear to the size of the data points. And of course, if you want to multiply the vector cost, it's going to multiply with another m. And then how often you need to do this? Well, you need to do it in every iteration. Therefore, you basically are going to multiply with another number L, which is the number of iterations. And in fact, you don't know how many iterations you will need to converge. But then based on kind of a street smart or street wisdom, you imagine that that number of iteration L must have been it should be much smaller than the number of n, hopefully, right? For example, if you have a n of a million examples, you don't want to run the iteration a million times, right? You probably run it 100 times. Okay, that's a big win because you have 100 over 1m, and that basically will be making this particular term way smaller than n squared algorithm. Okay, so that's basically the take-home message. You are really now introducing a heuristic which allows you to run a quadratic algorithm to the size of the data points. And that's actually one of the major advantages of a k-means algorithm. C-choice, as we just discussed earlier, it will play a huge impact, on the outcome. So you may want to try multiple times of random seeding, but again, you don't want to do it n times. You probably then do it like 10 times or 30 times. So as a just a folklore, in a typical k-means algorithm, people would try maybe anywhere from 10 to 20 kind of random initializations and run the iteration until convergence without really restricting. But you put a kind of a, how shall I say it, maybe a threshold of the maximum number, the L max, on the loop, so that if your iteration does not converge yet until before you reach the x, say x equals to say 100 or maybe 500, you just force stop this algorithm. Because again, the folk wisdom says that if you are really at a good spot of initialization, say for example, in this loss function, if you start from here, chances are you are going to converge pretty fast, right? The only reason you don't converge fast is because you are in a very awkward situation. Maybe in here, there is a shallow kind of, valley where you start to bounce back and forth. And that basically gets you to a non-conversion point. And you want to get all of that anyway. Therefore, you don't have to continue the iteration too long. Okay, so these are just heuristic and folk wisdom. I don't have a theory for that, but good to remember those tricks. All right. Well, now comes to the million-dollar question: how many number of clusters that we have to use. I see now it happens less often. In the past, when CMU or many other universities are interviewing a machine learning faculty, and when the faculty are giving a very exciting talk and so forth on say a unsupervised learning algorithm, oftentimes among the audience, a smart student or a very smart demanding faculty will say, "Aha, your algorithm is great, but how do you determine k?" Meaning, how do you choose the number of clusters, or how do you determine the number of features you want to collect? Well, this is a real hard question. And if you get too serious about that, you don't have an answer for it. Okay, it's a still very debatable kind of a thing nowadays with many different heuristics. So here I offered a few things that if you have to interview and face that question, it can make you smarter. Okay, one thing could be that I don't know what k is optimum, but I can choose a k to be anywhere from 1 to say some bigger number, and I'm going to do something called a cross validation, or some other kind of measure, okay, to determine whether the k makes sense, in which k gives you a better answer. Well, cross validation in here is a little bit ill-defined because it's unsupervised learning, it's not supervised learning. Therefore, you have to be a little bit more careful in designing cross-validating what and using what data, hold off data or what. Again, this is not the focus of today's topic. I don't want to dive too far into that. It's it's a slippery slope that you can get quite hairy, when we dig deeper. Maybe a cleaner answer, which does.
Someone just has a quick question. Someone said, what will be the loss for cross-validation?
Exactly. That's why I want to get into that, because it's becoming a very heuristic and a hairy thing that it depending on, for example, whether you have a bias in terms of a prior kind of number as under a distribution, or you say that number can allow you to define a proper intra-cluster distances over novel data points. Again, there are no theory for that. I don't want to dive too deep into that. Okay, I do want to say one thing that has a nice theory, which is about the non-parametric Bayesian inference. In there, the number of clusters k is treated as a random variable, okay, which has a infinite cardinality, meaning that it is literally from 1 to infinity in theory, right? And you can actually write down a posterior distribution, P of k, given everything else, during your inference step, so that you can pick a argmax of the k based on such a posterior. Okay, so this is known as a non-parametric Bayesian inference, okay, and also sometimes known as the Dirichlet process or Dirichlet process mixture. If you are interested, I can point you to a few papers about that. There are nice theories behind the justification and also the operation of that. And also this infinity sometimes make people very, very kind of worrisome if you are an implementer, because you have a finite memory in computing devices. You cannot keep infinitely many cluster centroids as placeholder. But the truth is that all you need to do is to keep whatever already is a concrete cluster having data membership already. And for those empty clusters that does not have memberships, you just can keep it symbolically and rather than physically, in your memory and so forth. So there are a few tricks in terms of how to implement this process. But at least this issue has been studied. There are, heuristic and more theory-oriented answers to this problem. But in practice, I tell you what, when you actually need to do clusters, I would say you just choose a good number. Okay, and for a pragmatic convenience, you choose a number to be conservative, say big enough. And then when you get a cluster back, if you see a good number of clusters are so-called very sparse, having only a few data points, that means that you are overshooting already. You can reduce the number from there. And you will be able to always hit a practically legitimate kind of a cardinality of the cluster problem, right? So that's how people literally implement typical clustering algorithms. Okay. Any questions?
Yeah, I have someone asking privately. In that probability distribution that you drew, the dots are the data, right?
Yeah, they are the data. In fact, it's more complicated than the data. Yeah, it's the data. It's also the parameters of of your clusters. The cluster may have a centers, right? And that actually also come from a Bayesian prior, with more likelihood or less likelihood. Yeah, if you want to be full Bayesian, everything in your equation is a random variable. Therefore, they will be all put in here. Again, again, if you are interested, you could read a few more papers. It's fun to read. It's a little bit mathematically challenging to read it, but still, welcome to give it a try. Any other questions? Okay. At least I hope by this point you know how to write a legitimate, clustering algorithm, using a k-means principle. Okay. Well, here we may want to even look a little bit further to talk about how to compare cluster outcomes. So what we just have the SD measure is a intrinsic measure, which is the loss function of your own clustering algorithm, right? Sometimes people may want to determine a few what they call the external criteria of the clustering algorithm, right? Well, there are a couple of different external criteria. One is that well, there may be some ground truths that the data should be clustered in a certain way. Okay, for example, I could imagine clustering, for example, animals. That maybe cats and dogs, you want to put them into the same cluster, and maybe fishes and crocodiles, reptiles should be in our cluster. I don't know. Maybe that's your way. You call them ground truths. Well, your cluster algorithm may agree or may disagree with you, depending on how you define the distance. If you count the number of legs, well, maybe that's going to give you the answer you want. Maybe not crocodile, fish versus say a dolphin, for example, right? So then you get a cluster with the dog and cats and the fish and dolphin. But if you specify a different distance metric, say their blood temperature, for example, well, that will give you a cluster that is disagree with your so-called ground truths. Okay, that's going to probably put dolphin together with dog and cats. Right? So ground truths we need to take it with a grain of salt. Another more quantitative, in fact, even with ground truths, how to quantitatively score that. And here I have a few things. One thing is known as the purity. It's a very simple measure. It's basically saying that, okay, you already have your ground truth labeling, say cats and dogs and the dolphins and the fishes and all that. And then now you are given a artificial clustering from the algorithm. And then you compute the purity, which is the maximum number of a single kind of label, ground truth label, appeared in the cluster versus the total size of the cluster. Okay, and that gives you the purity measure. Okay, and then you are going to now average them. Okay, and that gives you a single number. And sometimes this can be used to compare different implementations of the algorithm or different algorithms for clusterings. Okay. There is another more kind of sophisticated one, which look at not just the biggest kind of membership, but all memberships using an entropy measure. The entropy measure measures the disagreement of the actual label versus the artificial label, by your clustering algorithm. I'm not going to write the equation down, but if you're interested, you can Google it. Okay. All right. There are a few other partitioning algorithms which I believe is beyond the scope of today's lecture. But one of them, mixture-based clustering, will be discussed in depth in our next lecture. But I'm not going to discuss the self-organizing map and the fuzzy and algorithm and so forth. But if you are interested, here are some pointers to the papers for those algorithms. Okay, how are we doing on time? We have 10 minutes. Good. So any questions there? Don't quite catch the notation of the purity. What is WI? Let's see. Oh, okay. Thanks for pointing that out. Yeah, the WIs are, let me see. I need to remember. These are just the reference to the K clusters. Okay, it's a very, very kind of how should I say ambiguous notion. You could understood the W as referring to the centroid of the cluster, or the data membership of all points into the cluster. Yeah, it kind of just reflects the fact that your data points are now assigned to the K clusters, and this is a reference of their configurations. Okay, thanks. Other questions before I jump into a very quick discussion of the metric learning?
Actually, yeah. What's NIJ here?
Nij here. It's the, let's see. J, I believe, is the, hey, you are giving me a hard time. Basically, one of them is the actual cluster, say your K clusters. And the other one, either I or J, is the ground truth clusters that you have. Basically, you are saying that my data points from cluster J in the artificial cluster of a cluster I, something like that.
Is N, I mean, like, what is N though?
N is the
it's the number of members.
Yeah, the number of membership.
Okay, so it's the number. Is Nij the number of common members in the ground truth cluster and the predicted cluster?
Okay, let me give it a try. So you can imagine N. In fact, I'd rather you use this example to understand. It could be a little quiz. This example tells you what Nij is, but in here it's really about the cluster, the number of members from cluster J in the artificial cluster of I produced by the algorithm.
Okay, got it.
Okay,
yep.
Great.
Thanks.
Yeah, but I think you want to, all of you want to look into this example very carefully so that you can get it, okay? Because sometimes there is a different way of saying the same thing. I want you to be able to say it in your way rather than the way I used, okay? All right, I have another 7 minutes. I think it's still the number of points with the same color. Yeah, sure. With the same color, meaning that with the, in the ground truth clusters, yeah. I do want to mention metric learning, not because it's one of my earlier paper. It's because this is a modern topic that nowadays become a kind of a foundational algorithm for many of the applications. So imagine that you want to have some peculiar clustering problem, which is hard for you to specify metric. For example, imagine that these are data points, I give it to you. What are these corresponding to? Well, typically, if I don't tell you anything and you run k-means, you may run into naturally these two clusters, right? Because they elongate along that direction and they are connected. But if I have to force to cut them into two, I probably cut in the middle, right? But if I tell you that, well, these data points are kind of special, they are the GPS signals of cars on a two-way highway. If I tell you that, what do? Then you probably say, aha, it doesn't make sense for me to cut them into the middle. I probably want to group them by lanes, right? But how can I achieve that? I probably need to ask you, okay, please label all this. Well, the point is that I don't want to label it because I'm asking an algorithm, to run in an unsupervised fashion because I'm lazy or I don't have time or it's too much for me to label, right? So, and also how to articulate this metric that reflects the lane is also a tricky thing. You may be able to articulate that, don't measure the distance across the lane, but measure the distance along the lane, something like that. It's a little bit hairy to articulate when you run into a bigger problem, say image and other things. Right? So one of the things people, learned, to communicate this kind of knowledge is to give you examples. I will say, oh, hey, I don't tell you anything else. I will tell you that this point and that point are similar to each other. And that point and that point are similar to each other. And this point and that point are dissimilar to each other. I will tell you this, right? And I will give you maybe 3 or 4 examples, even though I have a data set of 1 million data points. So how can we use that to discover metrics automatically, right? So this algorithm allows us to do that, okay? Okay, so this slide has been explained already using the lane distance idea. I'm going to give you just a key equation that you can basically inspect to get the gist of this particular algorithm. But again, because of time limit, I'm not going to cover the details of the algorithm. The paper is online, can read it, right? So I'm giving basically a data set like this. Then in additional data set, I'm going to give you, this so-called side information that it is a small data set of pairs of labels or data points, which I call them to be similar. And this one, the dissimilar one, I could choose to give you a few, or I could say that anything that is not in a similar could be considered as dissimilar. That's also fine. Okay. So imagine these are probably cheap and inexpensive, side information that you can practically obtain from a trainer or from a data provider. Then what you do is to now define what we call a distance metric in the following way. It is known as the Mahalanobis distance. Okay, it's basically very similar to the Euclidean distance we just saw, but with a matrix. Okay, which provides a way that you weight different directions and also the correlations between directions. Okay, and this is known as a unknown kind of matrix. Okay, if this is a diagonal matrix, for example, if A is a diagonal, then it collapses to Euclidean distance. Okay, and then you are going to have a learning algorithm which does the following. I'm going to treat A as unknown. I'm going to learn such A that minimizes the metric between the data points that I call to be similar, and subject to a constraint that the data points that is dissimilar to each other in here never collapse. They should have a non-zero distance always. So that when I shrink and shrink, they will be kind of falling onto a ball that prevent them from further being reduced in terms of their distance. Okay, and A is positive semi-definite. Okay, so that's it. It's a very simple algorithm. And in terms of solution, well, it is first of all a convex algorithm. Therefore, there are no local minima. You can actually drive the A to a solution that you called A globally optimal. Okay, and in terms of the algorithm approach, it could be a gradient projection approach that every time you take this as a loss function and over a gradient, on A, and then you're going to satisfy this constraint by projecting the gradient into this subspace. Okay, so it's a very, very intuitive, easy algorithm for people to implement. And at the end of the day, you get A, which will augment basically your distance. Every time you compute the distance between data points, you're going to now use this equation with a newly learned A, which actually worked on transforming the data. For example, you can see a few geometric examples. Here are your original data points. Okay, and of course, I show the label or show the color, which is the ground truth label. In the algorithm, they don't see the color. Okay, and but I give them just a small number of side information as similarity and dissimilarity constraints. And you can see that after the A was learned, if it's learned diagonal, they can basically find out directions which maximally separate all these distances already. And if you only use a one dimension, in the data, again, it can still separate this, this data point in the cleanest possible way, right? So it's an automatic way for you to really determine which dimension in the data you need to pay attention to, especially in a problem like this, for example. If you use a naive way of clustering, if this is the data point, you are going to cluster like this, right? But if I told you that a data point in here and a data point in here are similar to each other, then the A matrix will automatically tell you that you want to discount the distances along this direction, okay, and pay more attention on the distance on this dimension. And at the end of the day, you can see the data collapse to this, which is that the distance along this way is pretty much collapsed and ignored. Okay, and that's because the side information told you that a particular dimension is more important than the others. And therefore, that dimension is preserved and this dimension is collapsed. And that makes the problem a lot easier. After this redefinition of the distance metric, you can still run k-means on top of it, or any other algorithms that is based on distance definition to achieve a convergence. Why this whole thing can be no less than 1, not 0? This is a very interesting question, but it is actually a more algebraic question. If I make this a trivial to be 0, then I can make the A arbitrarily small to shrink the data. Therefore, nothing gets separated. Right? In fact, it doesn't have to be 1. It can be a good number that allow easy algorithmic operation. 1 is just a convenience. It could be 0.5, for example. It could be 100. Okay. Any other questions? We're already over time. So if not, let's conclude today. And tomorrow on Wednesday, I'm going to cover the k-means, the EM algorithm, which is a more general case of k-means. But make sure that you digest today's material so that you know what k-means is about. And then we're going to have an easier time next time to proceed into the EM. Okay. All right. See you on Wednesday.